So, so last time we talked a lot about CFTs, about the bootstrap. And today we will change the gears a little bit. We'll go to quantum field theory for a while. And our logic today will be, today and in the rest of these lectures, will be the following. So the bootstrap that I described last time is a consistent framework. It's an axiomatic approach to conformal field theory. So in the old days, there were other attempts. So people have thought about other consistent frameworks to think about quantum field theory, other axiomatic systems. So most notably Whiteman axioms and Osterwalder Schrader axioms. And it's interesting to investigate what is the relation of those systems of the old days to what we are doing with the bootstrap. So can we derive those properties that people were postulating from our consistent framework, or should we accept them as an additional assumption? That's the question that I would like to think about. And so let us leave conformal field theory for a while, and let us think about quantum field theory. And I will talk about Whiteman axioms. So Whiteman axioms are formulated in Minkowski space. So it's precisely in agreement with the subject of my lectures. And so they enshrine the minimal properties that any quantum field theory in Minkowski space is supposed to have. So everybody more or less agrees that these are reasonable axioms. And they are quantum mechanical in nature. So unlike the bootstrap axioms that we discussed last time, which were kind of statistical mechanical in nature. So in Whiteman axioms, we really take the quantum mechanical point of view. So we assume that there is some Hilbert space of states. So on this Hilbert space, there's a Poincaré group which acts by unitary transformation. So we have a Poincaré group elements which are parametrized by translation and some rigid Lorentz transformation. And with each of these Poincaré transformations, we have a unitary operator acting on this Hilbert space, so which transforms it. In particular, we have translations which are represented by E PA. So this is P mu A mu. These are translations. Translations representation. So for a while, it's going to be pretty pedantic, but okay, little by little, I hopefully will come to some things that not everyone has seen in their life. And so let me just build some baggage here. Okay, so the one non-trivial assumption that one makes is that, okay, so there is this translation generator P mu. One can consider the spectrum of this translation generator, and one makes a very important assumption that the spectrum of this generator belongs to the forward null cone. So something that I will denote V plus bar. Bar means that it's a closed forward null cone. And okay, this assumption is reasonable because if you think that the theory, for example, if your theory contains some particles, then p squared is equal m squared, and it has to be non-negative. So this is the condition that the spectrum of p. So this condition that the spectrum of p mu in the general theory, when maybe there are no particles, but there is some spectral density, it all has to be contained in the forward null cone. Then further one assumes that there is a unique vacuum, which one denotes u, omega. And this vacuum is invariant under the action of the Poincare. Finally, one introduces local operators, phi of x. And okay, again, in our first lecture, when we talk about operators, they were not really operators, but they were just some fields of whom we were measuring some statistical correlation functions. But here, operators are really quantum mechanical honest-to-God operators acting on this Hilbert space. So these are quantum mechanical operators, and these quantum mechanical operators, they transform, they have this transformation property which encodes Lorentz invariance. So if you sandwich conjugate by UG, then this gives you rho of lambda phi of G minus 1x, where this is the irrep in which phi transforms, irrep of Lorentz, rho of lambda. So this is this property. And I guess the last property that I have to say is that there is causality. So operators at space-like separations commute. So I use the mostly minus metric on my Lorentzian space. And okay, in general, the theory will contain many local operators. So these Whiteman axioms, they have to be true for correlation functions of all local operators your theory will contain. But for simplicity, we can focus on just one local operator. And let's just again assume for simplicity it's a scalar. And let's also assume for simplicity that it has been chosen Hermitian. So phi dagger is equal to phi. This we just assume for simplicity. So these are the axioms. No, okay. Clearly, this quantum field theory is by assumption Poincare invariant. Poincare invariant. Yeah. So these assumptions are for Poincare invariant quantum field theory. So these Whiteman axioms are from the 60s. At the time, people didn't yet know that these exceptional things that you think. But what do you mean by non-local? What do you mean here by non-commutative superangles? Who cares about non-commutative superangles? Let me take a more physical example. For example, QCD is supposed, like if one day we will show that QCD really exists, it's supposed to satisfy these axioms. QCD will satisfy. Non-commutative, I don't know. I'm not considering here such weird things. Like any UV complete part of theories of particle physics that you may think of should quantum field theoretics should satisfy these axioms. Well, honestly, I don't know what non-commutative superangles really is. I don't care. Yeah. Yeah. Well, I'm not sure. Actually, these assumptions that you claim are so restrictive, actually what people have discovered is that they are not so restrictive at all. For example, one way that, as we will see in a second, is that there is a way to relate these Whiteman axioms which are formulated in Minkowski to other sorts of axioms which are formulated purely in Euclidean. So for example, if you are dealing with a theory which in Euclidean will have some path integral representation, then upon Wick rotation, you believe that you will get a theory which will satisfy Whiteman axioms in Minkowski. So even though it might look like I'm making some strong assumptions, actually, from a certain point of view, these assumptions are not strong at all. They are supposed to be naturally present. I have not convinced you because you are stuck up on this non-commutative super Young-Mills. Further, forget about super and forget about non-commutatives. Just think about physical theories which have been observed in experiments. Okay. Is there anyone else who thinks that these assumptions are very strong and they need to be relaxed?
Well, you assume unitarity, right? You could relax that.
I'm assuming, yeah, here I'm assuming unitarity, yeah, because quantum mechanics, you can only do it in unitary.
Last time you didn't assume unitarity in conformal field theory.
I did not assume unitarity, but at some point I was mentioning unitarity. I was mentioning reflection positivity, and so one thing that perhaps I have not emphasized sufficiently is that this relation between Minkowski theories, Lorentzian theories, and Euclidean theories, it's only going to be true. It only has a chance to be true if the theory in Lorentzian, if the theory in Lorentzian is unitary and the theory in Euclidean is reflection positive. If the theory in Euclidean is not reflection positive, I have not defined yet reflection positivity, but I will today, then I don't know what it means to continue it analytically to Minkowski space. You will get, sometimes people say, oh, well, you will get a Hilbert space, but with a non-sign-definite metric. Well, in mathematics, Hilbert space by definition has a sign-definite metric. If it's not sign-definite metric, you don't call it a Hilbert space. It's an abuse of language. Yeah. So we focus on unitary theories.
Minor question. You wrote causality, and then you wrote two equations, and then you said locality, and I got confused which one is which. And
I never said locality. It was Monica who said locality. So this equation is sometimes called microcausality, when the operators at space-like separations commute. I said local operators, 5x, which just means that operator which lives at a point.
lives at a point, but it's an operator acting on H.
It's an operator acting on H.
So what does it mean to live at a point?
Well, it means that if you compute if you take a string of these operators, well, I'm not now going to compute correlation functions. So these correlation functions are going to be functions of n points. That's all. In the theory like Young-Mills, I would only, so this definition would only apply to gauge invariant operators. Well, I'm not saying that this theory does not contain any other operators. I have not made any completion. I have not made any statements about other interesting observables that might exist in this theory, for example, like Wilson loops. But I'm going to focus on these particular observables, on local operators and their correlation functions. Any other questions? It's great. So even Whiteman axioms evoke so many questions. So I'm very happy. It means that it's not boring. So, okay. So then we consider correlation functions. Actually, I have lied to you a little bit. So let me complete the discussion. So we consider correlation functions of these local operators that I introduced.
I'm sorry. I think so. If you're looking at Minkowski spacetime and you're defining phi of x, and you think of like having like a, I'm going to use these words, but I don't want you to interpret like a fiber bundle of like spaces, and this H is really like the rectangle of these Hilbert spaces, and phi of x just acts on one of these fibers. I still don't understand this locale, like a local operator. What makes it different from any other operator in V of H?
What makes it different from any other operator?
If I give you any operator on H, how can I tell if it's local or not? And my only guess is that H can actually be decomposed into a bunch of like Hilbert spaces, and this one happens to just act on one of those pieces.
Well, I'm not.
But like imagine.
I mean, let's just proceed by examples. You say, how would you know that the operator is local or not? I mean, we know field theory, right? A little bit. We know if you say if your theory, we have a certain toolkit how to construct things that we believe will satisfy these axioms, even though in many cases we cannot prove this. Take some path integral. In this path integral, there are going to be things like phi of x. Just construct something of this phi of x. This is going to be a local operator after you renormalize and everything. If you take a Wilson loop is not going to be a local operator. So which property will it not satisfy if you take a Wilson loop operator? Well, many of these properties, like, okay, I will not be able, so I take a Wilson loop. Wilson loop is parameterized by a curve. It's not parameterized by a point, by a curve. So, I mean, I don't know even how to write down this property. Causality will also fail because Wilson loop, if you try to associate Wilson loop artificially with some point, for example, let's take the center of the loop and let's pretend that the Wilson loop is somehow a local operator sitting at the center of the loop. Well, causality will clearly fail because you can take a loop where the center is space-like to some point, but there are some parts of the loop which are not space-like, and so it's not going to commute. So you see that the Wilson, just by staring at an operator, you already see if it has a chance to be a local operator or it's clearly something which involves more space-time points. So let's not try to overdo it on the mathematical side. Yeah?
So just to be clear, the word locality so far has never, there's no notion of locality that has ever shown up in the application so far. We just have a family of operators labeled by points in spacetime.
Yeah.
And so far they have to satisfy this commutation relation.
Yeah. Yes, and I will not introduce even the notion of locality in a stronger form.
So literally any family of operators parameterized by spacetime are characteristics.
Yeah.
One satisfying these conditions.
The one who satisfies this one computation relation.
But you have to be a bit careful because, I mean, given a local operator, you can, for example, try to smear it. If you smear a local operator, as I will do in a second, it's a smeared local operator is not a local operator anymore. Even though if you like smear it over some neighborhood of a point, you can try to say that the smeared local operator is a local operator which lives at the center of the region over which you smear it, but that would be wrong.
But my understanding is that the reason that would be wrong is because then the causality axiom would fail.
That would causality would fail, and also this axiom has a chance to fail because when you smear it, you will smear it with some function, and so that function, for this to be to have a chance to be true, it has to be a Lorentz invariant function. And if you like smear out over some ball is not Lorentz invariant, so it will fail.
So if I prefer to, I can ignore all of these philosophical bending statements about smearing and whether an operator is really a point and just say if I have operators that are satisfied, they're written by action.
Yeah.
By these conditions, and it's fine.
Yeah. For all we are going to do, we will just I gave all these examples, like Wilson loop is bad and local operator is good and so on, but from this moment on, you will not really need to know where this operator comes from. Yeah.
Okay, so you decide to concentrate on the local operators in the field. So do you understand what subspace, subset of space they start, like random or random or something, or what do you generate with the action of the local operators, and are you missing part of the physics space? Is there any statement? I mean, I'm happy if you want to say some subset of
It's a good question. Sometimes people add an axiom that by acting with local operators, you can generate a dense subspace in the Hilbert space. You may try to discuss if that axiom would actually be a good axiom in gauge theories or not. But I won't use that axiom, so yeah, I'm not prepared to make any sharp comments about it. So I was considering these correlation functions. Okay, this notation is equivalent to the bracket notation, but a bit more economical. And so these correlation functions are called Whiteman functions. And just to stress their difference from some other correlation functions that we encounter in Minkowski space quantum field theory, which are time-ordered correlation functions. So Whiteman functions are not time-ordered correlation functions. So what's the difference? Is that in the Whiteman functions, like suppose that I fix, here I'm considering all operators identical, but suppose that I take different operators. So I fixed the order of operators in which I multiply them, phi 1, phi n. But then I vary each argument, each space point argument of each of these operators over the whole Minkowski space. For example, when x1 becomes to the past of xn, I don't reorder the operators. So if I were to define a time-ordered correlation function, I would have to stick in some theta functions in my distribution, which would reorder operators when x1 becomes to the past of xn. In the Whiteman function is a more elementary building block. You say, before I start like multiplying by theta functions and see what happens, let me just consider a simpler case where I allow x1 and xn vary over the whole Minkowski space independently, and I don't try to reorder operators. Let me try to understand this first, and then if I understand this, I can think about time-ordered functions next. So I'm only going to talk about Whiteman functions. And so one important axiom which I have not yet said is that we would like to know something about these Whiteman functions, about their regularities, regularity properties as functions of x's. So these are functions of x's. And in particular, I would like to know what these functions do where points x1, xn, when they collide pairwise. And so there is an axiom which says that this thing should be a tempered distribution. Now, what does this mean? Well, it means that, let me introduce notation for this thing. It's W of x1, xn. Well, it means there are various equivalent formulations, but what it means is that if I take an integral, if I take this W and x1, xn, and I pick smooth functions f1 of x1, fn of xn, and if I integrate on all points, then these integrals should be finite. It should be well defined and finite, provided that these smearing functions fi are nice functions. So now we have to define what nice functions means. And the distribution that is very convenient for our property is the Schwarz class function. So Schwarz class function means a function which is infinitely differentiable and decays at infinity faster than any power of a polynomial together with all of its derivatives. So the technical reason why this Schwarz class is a very nice class is that it behaves nicely under Fourier transform. So if you take a Schwarz class function, you take a Fourier transform, you get a Schwarz class function. Well, for example, another class of test functions that people use are compactly supported functions, but if you take a compactly supported function, take its Fourier transform, it's no longer compactly supported, and this is not convenient. But now let's go back to this condition. So what does this condition say? It says that, well, I don't know. So basically it says that these singularities where points collide pairwise, they have to be resolved in some way to make these integrals well defined. You can rewrite this in a different way, this equation. Let me introduce, instead of phi, I can introduce a smeared operator. Let me call it phi of f, which is just an integral phi of x, f of x dx. And so what this axiom then says is that the following thing, so I can rewrite equivalently this integrated correlation function, integrated Whiteman function, as omega phi of f1, phi of fn omega. So, this is what we call a smeared operator, phi of f. And so what this axiom then says is that smeared operators. So I was a bit lying to you when I called phi of x an operator. So the true operator should have the property that if it acts on a vector in the Hilbert space, then it gives you back a vector in the Hilbert space, which means that it should be something which has a finite norm. Yeah?
Is this completely analogous to how in ordinary quantum mechanics, when you take a wave function, you can decompose it into its position eigenstates? They're not really eigenstates in the Hilbert space, but you can still smear your wave function as an integral with respect to these delta functions.
No, it's worse than in quantum mechanics, because in quantum mechanics, the position operator in quantum mechanics or the momentum operator in quantum mechanics, they are operators, they're unbounded operators, meaning that they are not defined on the full Hilbert space, but there is a subspace of the Hilbert space such that if you act on it, then this operator is defined. And this subspace it contains almost all functions, but not all of them. Here we have here in field theory we are in a worse position. So phi of x is much worse, is a much more singular guy than the position operator in quantum mechanics. So why is this singular? Because even if it acts, so for example, let's take phi of x and let's act on the vacuum.
I was actually comparing phi of x to delta x.
Phi of x to delta x.
Eigenstate of
Yeah. Yeah. You could. That analogy would be probably a good one. That's a good one. So phi of x. So what I want to say is that phi of x acting on the vacuum. So let's consider this state, and let's compute its norm. So the norm of this state is okay. It's omega phi of x omega. So it's a 2-point function of phi at coincident points. So it's infinity. It's not defined. So we see that phi of x acting at a point is even if it's you apply it to the vacuum, you already get something which is not in the Hilbert space. On the other hand, if you take a smeared, if you take phi and you smear it, then you have the property that acting on the vacuum with an arbitrary string of these operators, of the smeared operators, you get something which is still in the Hilbert space. So, the way people usually state it is that phi of x is not an operator, but it's an operator-valued distribution. But okay, we don't need to use. We won't have to use such a fancy language. Okay, so now for what is going to happen is that from now on, you pretty much can forget about these operators phi of x. Well, I mean, from time to time they will appear. But our main focus is going to be on the correlation functions w. So we will think about the correlation functions w and about their properties. So we have to understand, because thinking about these operators is a bit painful. So we would like to derive some properties of these functions w and just think about those properties and not think about operators anymore. So what are these properties? I already, so far I defined these functions w. What are their properties? What kind of properties do they have? Okay, that they're distributions, it's an axiom. Another thing that you can easily understand is that they will be Lorentz invariant functions, because you can move operators in Lorentz invariant way, and so these w's will transform in a Lorentz invariant way. Now, there are two more properties which are a bit more subtle, so let me derive them. perhaps let me state them, and then because some of these things that I'm talking about are quite intuitive from the physical point of view, but I don't want to waste too much time on that. So there are two more properties that we will need. So the first property is this. So let us, instead of talking about this function w, we can, since w is translationally invariant, we can go to this function w. So this is going to be script w, which is a function of n points x1, xn. And I can pass to this function straight w, which is a function of xi1, xi n minus 1, where x's are just differences. Xi equals xi plus 1 minus xi. So instead of studying w, script w, I can study this straight w. So let me take this straight w, and let me take a Fourier transform. W hat of q1, qn minus 1. Now, notice something very important is that, okay, of course, in quantum field theory, we use Fourier transforms all the time. Now, if you try to be mathematical, then you have to ask, okay, this W is a singular object, so in which sense does a Fourier transform exist? And here we are very helped by the theory of distributions, because it's a property of any tempered distribution that if you take a tempered distribution, then the Fourier transform exists, and it's also a distribution. So you are in business, we can talk about Fourier transform, and it's if W is uniquely defined, then W hat will also be uniquely defined. There is no ambiguity. Now, sometimes when you do quantum field theory, you have to do a Fourier transform of some function, and then you say, well, let me pick some regulator, and then the integrals are finite, and then I compute the Fourier transform. You get some answer. And then somebody else picks as a different regulator, does a Fourier transform, and again gets the same answer. Why do different regulators get the same answer? I mean, it's always like a magic. Well, they get the same answer because the Fourier transform exists and is unique by the property of the distributions. That's the reason behind all these coincidences. Now, this Fourier transform W hat, it has a very important property that the spectrum, so we can compute not the spectrum, we can compute the support of this distribution W hat, so where is it non-zero? And the claim is that this support is contained in, again, in the product of forward null cones. So if it's non-zero, this W hat, only if all of these vectors, q1, qn minus 1, each of them lives in the forward null cone. So is this, before I prove it, I would like to see if this is if this sounds physically reasonable or not. This is the consequence of the axioms. This is going to be a consequence of the fact that the spectrum of P mu is in the forward null cone. No, it means Q1 is a vector. So this has to be in the forward null cone. They don't have to be mutually in forward null cones of each other, but each of these vectors, which are dual to the differences of coordinates, they have to be in the forward null cone. So this is a very strong restriction on the structure of the Fourier transform. Okay, I'm not going to give a full proof, but just to give an idea. So you take this W of xi1 Xn. And by moving operators around, you can write this W in the following form. So you move the first operator to 0, and then here you have to insert e to the p dot xi1, and then the second operator to 0, e to the ip dot xi2. I'm sure you have seen such tricks in quantum field theory textbooks. And so you see here on every time between two operator insertions, we have this insertion of e to the ip. So every point from the spectrum of p, like let's suppose that there is some point where this spectrum of p is non-zero, some element q in the forward null cone. Then you can view this as an element which contributes to the Fourier transform. So this already has the form of, it looks almost like the Fourier transform, but you have to integrate over the spectrum of p in each of these points. So usually the way we argue it is that we say, okay, let me insert here the full basis of states, q, and e to the I Q1. So that's how we usually argue in quantum field theory. So you see, I get a representation of my correlation function as an integral over this momenta Q1 and the exponential factors, which are precisely the same ones as I have in the Fourier transform. And what I now have to say is that this resolution of identity, so all the states in my theory, this is the spectrum of p, they lie in the forward null cone, so I naturally get a representation where all q's are in the forward null cone. So this is the physics proof of this statement. Now, if you want to give a mathematics proof, then you have to deal with the fact that p is some operator and there's some spectrum. It's a bit more complicated, but in the end of the day, that's what's going to happen. So this is called spectral property. P is acting on all of H, yeah.
And it is an example of a non-local operator, correct?
Yeah.
Okay.
Yeah, it's a good example of a non-local operator. Also unbounded.
Right.
Yeah. So that's one property of the Whiteman functions which is very important. And another property, actually the last one that we will need, is derived as follows. So I can consider states. Let me consider a state psi, which is obtained by taking a string of local operators. And now I'm going to smear them, but okay, until now I was smearing each operator separately, but now I'm going to smear them jointly. In fact, you can show that this operation is also permissible. So this is a state, and now I will generalize this a little bit. I will consider some finite linear combination of such terms from 0 to n. This is a state in my Hilbert space.
Sorry, is that x1 through xn just a coefficient?
Yeah, this is some scalar function, or some complex function.
Okay.
Smooth complex function of n variables. So this belongs to Schwarz class in n variables.
And you want to sum over the number of variables?
Yes.
I don't understand that.
Uh,
I guess you want to integrate.
no, I don't want. Yeah, sorry. Yeah, of course I want to integrate. Yeah. It's dx1 dxn.
I think you have too many n's. I'm just confusing you. Little n's. Are you abusing some notation?
No, I think no. I think at this point I'm not abusing anything. I have so. Yeah, what's the problem here? There is a function of n variable which I call fn. Now, for each n, I take this function, I multiply it by n local operators at point x1, xn, I integrate. So I get some term, some element in my Hilbert space. Now I take a sum of these elements for n ranging from 0 to n. So for each sequence f0, f1, fn, I construct this element psi.
And are each of your f's, do each of your fi's have n inputs, or do they have I inputs?
Yeah, fi has I inputs.
Okay.
So why did I do this? Because I would like to now impose the condition that this state psi has a non-negative norm. So once I have this condition, then so I would like to write I would like to write this condition in terms of these functions fn. So what am I going to get? I'm going to get that. So let me write down the answer. So I'm going to get a sum of nm Whiteman function of order n plus m. And this Whiteman function is integrated, let me write it schematically, over fn complex conjugate fm dx1 dx n plus m. Because you see, I have this state. Let me just analyze one term here. I take this state. It depends on n operators. I take a scalar product with another state which involves m operators. So I have a correlation function n plus m Whiteman function, and then I have to integrate this Whiteman function with the product of one f function and its complex conjugate, which has m arguments. So I get something like that. So this has to be non-negative. And this is called positivity condition. So what I have shown is that for any sequence, for any finite sequence of functions f0, fn, if I compute this particular double sum, which is a finite sum, because I'm assuming it's a finite sequence, it's a funny double sum to compute, which involves Whiteman functions of order ranging from 0 to big N plus big M, I should always get something non-negative. Now, what was the purpose of all this song and dance is that now it turns out that I can forget about the Hilbert space. Namely, there is this theorem which is called Whiteman Reconstruction Theorem, which says the following. Suppose that I'm given sequence of Whiteman functions Wn, which are temporal distributions and which satisfy all the conditions that I have written down. So they satisfy this positivity condition, they satisfy the spectral condition, they're Lorentz invariant. Actually, something else that I forgot to mention is that they should be symmetric at space-like separation, which is a consequence of microcausality. So if I have this sequence of Whiteman functions, then I can construct everything else. So I can construct the Hilbert space, I can construct the unitary representation of Poincaré acting on this Hilbert space, and I can construct my operator value distributions phi of x, which would give rise to these Whiteman functions.
I'm sorry, but I think that you need to assume simplicity to write this. Otherwise, you have to assume that the application of phi on the vacuum are dense and in that space. Otherwise, how you can get back the word in that space?
Well, no, I disagree. So indeed, there are some. There's no claim that you get the whole Hilbert space.
Okay.
The claim is that you get enough of the Hilbert space
Okay.
so that if you work within this sector, you get back precisely the same Whiteman functions. Then there may be other sectors of the Hilbert space that you will not be able to explore. But this is natural. Like for example, so the theory may contain tons of Whiteman functions. Suppose that somebody is evil and gave you not the full set of Whiteman functions, but just a subset. Then you will still be able to construct a subsector of the Hilbert space, which is sensitive to these Whiteman functions, and then you can work on it. And then you can ask the next question: is this the full Hilbert space or not? But okay, this theorem sounds a bit like magic, but in fact it's not magic at all. I mean, the proof is a bit of a cheat. So the way this theorem is proven is that, okay, you know that the theory should contain this state psi. I mean, should meaning. Suppose that you want to do this. You know that the final theory should contain this state psi. And each state psi is parameterized by this function, by the sequence of functions f0, f1, fn, and the norm is given by this. Well, you can turn this logic around and you say, well, I'm going to posit that my Hilbert space elements are parameterized by a sequence of functions f0, fn. I'm going to introduce the norm by this formula. Well, that may not be a complete Hilbert space, but you complete it, and then you follow the nose and you reconstruct the unitary representation of the operator. So it's not a hard theorem to prove, actually. It's an easy theorem.
So this, on the left-hand side, the assumption is that this positivity condition holds for an arbitrary f?
For arbitrary Schwarz class f's of finite sequences. It's not a hard theorem to prove, but it also kind of liberates you from the necessity to think too much about Hilbert spaces. You can just think about distributions, and this is equally good.
But so you construct states which are parameterized by your f0, f1, fn.
Yeah.
But you have to model by some identifications of these states with one another.
As usual, when you complete the Hilbert space, there are going to be some states which have zero norm, maybe. If you're unlucky, then you have to mod out of them, but this is a very standard procedure. Like from the Hilbert space technology point of view, it's a very easy theorem to prove.
So, the thing after the bar on the right, is that just a retracing of the thing on the left? Or are you saying that this is the positivity condition?
Yeah, when you derive it, you just say that psi is equal to the sum. So it has to be positive. Yeah.
Oh, I see. So wait.
it was not one of the Whiteman axioms. It was our axiom was that so the Whiteman axiom was that if you take a vacuum and you act on the vacuum by a string of smeared operators phi, you always get a state in the Hilbert space. There was such an axiom. Now, if you get a state in the Hilbert space, you have the right to ask, well, you have the right to compute the norm of this state, and ask, well, is it positive or not?
It always is positive.
It has to be positive.
No, but by definition.
By definition of the Hilbert space, it has to be positive. And now I'm just expressing what it means in terms of the Whiteman functions. Okay.
So there's, so the expression on the top of the,
You could call it not condition but positivity property. Maybe that would be better. It's a property of the Whiteman functions that they satisfy this inequality.
the line at the top of the course, the thing inside that integral, the product of dx1 to dxn, is really doesn't mean anything, right? Because there's no effective product of the integral.
Yeah.
So are you saying one of the ways that the axiom is this extra piece of data, which is the thing that turns the scalar operator in a function into a space on a given space, which is the effective interpretation of that integral.
Yes. I mean, there are some steps that I'm missing because Whiteman axioms say that you should be allowed to smear each of these operators independently. But it doesn't tell you that you should be allowed to do it jointly, but it's an easy exercise to show that actually you can.
Ah, you can. Okay.
Yeah.
So this print, if you interpret that way, you're using control by itself.
Ye-
Not extra data.
Yeah, it's not an extra assumption.
And then once again, it's just pure reasoning without extra axiom that leads you to the fact that this logarithm, this e that you get from this procedure is actually equal to that.
Yeah.
Okay.
Yeah. So what has happened? Just to summarize, so with the Whiteman axioms postulated Hilbert space and unitary representation. Then we derive some properties of Whiteman distributions. Actually, you can say Whiteman functions or Whiteman distributions interchangeably by abuse of language. And then we reverse the logic. We say, starting from properties of Whiteman distributions, we can actually construct a Hilbert space. So let's just forget about Hilbert space and talk about Whiteman distributions. And from these Whiteman distributions, the first thing that people usually do when they lay their hands on Whiteman distributions is to construct their analytic continuations, which is what we would like to do because we would like to go to the Euclidean space. So analytic continuation.
I'm sorry, I have one more question about W. Is W2 of F1 comma F2 equal to W2 of F2 comma F1 for all F1 and F2?
Well, here I'm considering W's of identical operators. So because I have all n operators are identical. Phi of x1 is the same operator as phi of xn. It's the same phi.
I'm asking if you can interchange the two. No, arbitrary.
So-
Not just spatial separately, just arbitrary.
So W2 of x1, x2, is it equal to W2 of x2, x1? No, it's not. It's not. It's not in general equal. Yeah.
It doesn't seem like you just associate functions to these states because functions are commutative, and you seem to have like a non-commutative algorithm.
No. What do you mean a function is commutative? It's not. I mean.
They look like functions.
I mean, let me take a function. Let me take a function sine of x plus cosine of y. Is this a function of x and y?
I'm asking when you take these functions f0, f1 to fn, you create a state psi. You declare that to be your state. But is that the same state as, for instance, f1, f0, comma f2, comma fn?
not the same, because f0 is just a number, and f1 has one argument, fn has n arguments. So
0 was a bad choice.
yeah.
The point is, if you swap these functions, you'll get a different state.
You cannot swap the functions because each of them has n arguments. The function number I has I arguments. You cannot swap them.
Maybe the notation is not clear. You should write the explicitly.
In this equation. Okay, this is important, so I'll do this. Times fn x n plus m.
I think for the first function, you can start the order of the verb, which is step
Yeah, you're right. Sorry, it's good that we wrote this explicitly. Thanks, Yoshin. What's the time? I think people are exhausted, so maybe we should make a pause. The continuation is obtained starting from this formula, so W xc1 xn. So this is a trivial formula, q1 W hat q1 qn e to the sum. So we have this formula. And what now we would like to do is that we would like to take these xi's, which are in this formula are real vectors, and we would like to give them an imaginary part. So we would like to continue xi's, xi from Rd to CD, but not to the whole of CD. So the claim is that if we take imaginary part of xi I belonging to the forward null cone, this time the inside of the forward null cone, then the analytic continuation is going to exist and it's going to be, well, analytic. So the claim is that Whiteman functions can be considered as analytic functions, provided that imaginary part of xi, each xi lies in the forward null cone. So they are analytic functions in that region, and vice versa, if you go from that region and if you approach the real Minkowski space, the real Lorentzian space, you will recover the original Whiteman distributions as boundary values of those analytic functions. So how do you see this? Well, naively, it's very easy to see. So you say, okay, what do I have here? I know that, so dq1, dqn, I know that the support of each of the q, each of the q where w hat is non-zero, it belongs itself to the closed forward null cone. So if now I give xi an imaginary part, then what am I going to get here? I'm going to get here, so there is some forward null cone where I'm integrating each of the q. belongs to this forward null cone. So if I give psi an imaginary part which is also in the forward null cone, then you get I times I is -1, so you get something which is a decaying exponential, decreasing exponential. As a function of q. If psi is in the forward null cone. So what we have here is that we have w hat, which is integrated against the function of q, which is a decreasing exponential in this direction. Well, and then in other directions, it's still an oscillating integral. So now in physics, we say, well, we had an integral, it made some sense. Now we're stuck into this integral, a decreasing exponential. Of course, it still makes sense, and it defines something which is analytic. That's the physics argument. Now, if you want to be mathematical, you have to work a bit harder, but not really much harder. What you do is that, okay, you say here I have some function in the null cone, in the light cone, which is a decreasing exponential, and now you have to extend this function a little bit outside of this light cone, for example, so that it has outside of the light cone, it has compact support. Not compact, but it doesn't extend too much of the light cone. And now we can write this this integral as a result of applying w hat to some function which is decreasing in all directions. So you see, if you apply w hat to this exponential, to the oscillating exponential, then you get a w hat as a distribution. You apply it to exponential, you get a Fourier transform, which is also distribution. But if you have here under the integral some function which is decreasing fast in all directions, then you get w hat applied to a test function. And w hat applied to a test function is no longer a distribution, is already a number. So what this argument shows is that w at such x's, first of all, is a number, so it's a true function, it's no longer a distribution. And then you can also show that this distribution, this function analytically depends on coordinates inside this null cone. So that's this is the argument, basically. So this is the argument to show that this analytic continuation exists. Actually, the set of these xi's which belong to the forward null cone, it's called sometimes forward tube. It's just some terminology. So what else can we say? What can we say about this? What can we say about this analytically continued Whiteman functions or Whiteman distributions? Well, one thing which we can say about them is that once you analytically continue them, they remain, of course, Lorentz invariant. So analytic continuation preserves Lorentz invariance. So we have W of lambda xc is equal to W xc for lambda in the Lorentz group. But actually more is true, even more is true, because not only this equation is going to be valid for lambda in the Lorentz group, but it's also, so now we have this Lorentz group which acts on x's, and x's have now imaginary parts. So you can now try to act on x's which have imaginary parts, not just by Lorentz transformations, but by complexified Lorentz transformations. So, but also complexified Lorentz. So what's complexified Lorentz is, it means that you consider matrices which still satisfy this condition lambda t eta lambda equals eta, but now the matrices can be complex matrices. So this is the group of complexified Lorentz transformations, and this equation will still be true.
Can we use transpose, not complex?
We use transpose.
Okay.
We use transpose. So that this condition is an analytic condition on lambda. Now, now you can play various games which people have played with a lot of glee in the 60s. You can say, well, I have these lambdas which are complexified, and I act with them on x's. So xi lies in the forward tube. If I act with a complexified Lorentz transformation on xi which lies in the forward tube, actually you may get some other xi which is not in the forward tube. So you can use this equation to analytically continue W to an even bigger domain, which is called extended tube. And so you can try to find the biggest region where W is going to be analytic. We are not going to play this game. We are only going to, because our goal here is to continue analytically to the Minkowski space, or to the Euclidean space. This is the only analytic continuation we care about. So for this, the extended tube is enough. No, the forward tube is enough. You don't need to go to the extended tube. So we are interested in continuation to Euclidean. And this is, so Euclidean time tau is related to the Minkowski time t by this formula, t is equal minus I tau. So this is Euclidean time. So if you want to know simple mnemonic rule, how to remember the sign of this equation, so how is Euclidean time related to Minkowski time? Because sometimes it's hard to remember. Is it like plus IT or minus IT? Then there is a simple mnemonic rule. So what you need to do is that one thing that you do have to remember is that the Schrödinger evolution operator is e to the minus IHT. It's something that you unfortunately have to remember. And by the way, there is nothing sacred about this minus I. It's just Schrödinger fixed this in the 20s when he was writing his Schrödinger equation. So we are stuck with this minus I. But once we are stuck with this, then the condition is that it has to go to e to the minus h tau, so that you get a decreasing exponential as a function of Euclidean time. And then this fixes this relation between imaginary and between Minkowski and Euclidean time. So given this, we define Euclidean correlation functions, which are called Schwinger functions, which are defined at the positions tau 1, x1, tau n, xn, which are now Euclidean sets of coordinates. They are defined as Whiteman functions W at the positions minus I tau 1, x1, minus I tau n, xn. So now let us suppose that tau 1 is larger than tau 2, larger than tau n. So this is a curly W function. We would like to compute this x's, xk, which are the differences of coordinates. And so xk is so xk has been defined. Now, correct me if I'm wrong. So Ck has been defined as xk plus 1 minus xk. So imaginary part of Ck is equal to tau k minus tau k plus 1. This is the time part, and the special part is just 0. So this vector Ck, the imaginary part, is clearly in the forward null, in the forward light cone. So this belongs to the V plus. And by the previous arguments, this Euclidean correlation function, Schwinger function, this is just a name, is going to be analytic in at these points, tau 1, x1, tau n, xn. So what this argument shows, okay, it defines the Euclidean correlation functions, and it shows that they are analytic at non-coincident points. Because I'm assuming that I took n points actually. I took n points and I ordered them in a particular position, tau 1 larger than tau 2 larger than tau n. So, okay, there are some extra steps that need to be done in order to complete this definition. For example, what I would like to show, what can be shown is that given that W curly W is a Lorentzian invariant, I would like to show that the Schwinger functions are invariant under Euclidean rotations. So how this comes about? Well, this comes about because if you take Lorentz group and you take complexified Lorentz group and you see how the complexified Lorentz group acts on these sets of vectors, on this set of coordinates minus I tau 1 x1 minus I tau n xn, you discover that this action is the same as the action of the rotation group. So the complexified Lorentz group becomes under this transformation rotation group. Another thing that you would like to show is that in order to define the Schwinger functions is that we chose one preferred direction which we called tau, and then other directions which we called x, and we Wick rotated, so this transformation is called Wick rotation, with respect to tau. But we could have chosen a different action, a different axis with respect to which to Wick rotate. So we would like to show that this would give exactly the same value for the Schwinger function. So this can be shown using rotation invariance, because you can always rotate a little bit, and then the Schwinger function remains invariant, and then by a sequence of rotations you can always reach any possible axis from one axis. So what else would we like to know about Schwinger functions? So we would like to translate the properties of Whiteman functions that we had to the properties of Schwinger functions. The analyticity property of Schwinger functions was crucially a consequence of the fact that Whiteman functions satisfied spectral property. So we already used that. We used the fact that the support of W hat was in the forward light cone. So Whiteman functions had this other property, which is the positivity property. So it's natural to ask what would be the corresponding property for the Schwinger functions. And so this is going to be something which is called reflection positivity. Let me describe this. So Whiteman functions are invariant under if you analytically continue in the full forward light cone. There are going to be some complexified Lorentz transformations acting on those complexified vectors. Now I'm performing a more restricted analytic continuation. I'm just analytically continuing in the time variable. Now you can ask, first of all, which complexified Lorentz transformations preserve vectors of this form, of the form minus I tau x minus I tau n x, and what do those complexified Lorentz transformations do when they act on such vectors? The claim is that the complexified Lorentz transformations which preserves vectors of this form are exactly Euclidean rotations acting on tau x. You don't get more, you just get a clean rotation. So, reflection positivity. I will consider a special case, and then once we do it, I will generalize. So the sufficiently representative case that I'm going to consider is the case of the 4-point function. So I take a 4-point function w x1 xn x4, and I chose to write it in this form. So using translation invariance, I can move points around, but this time I chose to put the time to 0, but I don't care about moving the special coordinate of my operators. So I write it as phi 0 x1, and here I have e to the minus IH t1 minus t2. So phi of 0 x2 e to the minus IH t2 minus t3, phi of 0 x3 e to the minus IH t3 minus t4, and finally phi of 0 x4 acting on omega. So this is for general axis, but now I would like to first of all analytically continue. So I consider now Schwinger function analytically continued at Euclidean points. Well, I'm not going to write them, but it's going to be omega phi 0 x1 e to the minus h tau 1 minus tau 2 to the minus h tau 2 minus tau 3 to the minus h tau 3 minus tau 4 So now I would like to consider a special case where x2 is the same as x3. So let me write here x2 is equal to x3. I just grant me this wish. And x1 is equal to x4. That's the first thing, that special thing that I would like to consider. And then I would like to consider also a case where, so I have to take tau 1 larger than tau 2, larger than tau 3, larger than tau 4 to have an analytic function. But I'm also going to assume something about these points. So I'm going to assume that the times are symmetrically distributed. So I'm going to take tau 1 larger than tau 2, larger than 0. And then I'm going to take tau 3 is equal minus tau 2. And tau 4 is equal minus tau 1. So once I assume that, my configuration of points is basically is completely mirror symmetric with respect to this line tau equals 0, because x's are the same and tau's differ just by the sign. So this is point x1, x2, x3, and x4. So once I do this, something magical happens here. So what I can write this, continuing this line, I can write my correlation functions as omega phi of 0 x1. So let me write it like this. I can write it as psi, where psi is going to be equal to e to the minus h tau 2 phi of 0 x2 e to the minus h tau, well, this tau 3 minus tau 4, the point is that tau 3 minus tau 4 is now equal to tau 1 minus tau 2. So I can write this tau 1 minus tau 2 phi of 0 x1. So for this particular configuration of points, I managed to find a state psi so that the correlation function is actually equal to psi. And if this is true, it has to be non-negative. So one way the reflection positivity is sometimes stated is by saying that if I take an endpoint function of even order and I arrange points in a reflection positive configuration with respect to some plane, then this Euclidean correlation function has to be non-negative. That's one way to state this property. But this is not the most general, and this is not the full way to state this property. Because here I'm dealing with just one correlation function. So I'm not using the full strength of the positivity property of the Whiteman functions. If you remember, the positivity property of the Whiteman functions was formulated as a condition involving not just a single Whiteman function of positive order, but of even order, but it was a sum, a double sum over m and n. So now you can guess that I can reformulate that condition in a way as a condition on Schwinger functions, similar condition on Schwinger functions. So let me write it down. And I'm sure you will agree that it's very convincing. So I do it like this. I define a reflection operator theta, which takes tau x and maps it to minus tau x. And if this operator theta acts on some function of n points, then it maps it to a function, the same function, where I reverse the order of the arguments and flip each coordinate. And so the full reflection positivity condition says that the following sum has to be non-negative. So I take Schwinger functions Sn plus m. I sum over nm, and I integrate them over theta fn complex conjugate tensor product fm. So I pick, again, so here I'm assuming that I picked some sequence of functions f0, fn. What do I have to take, what do I have to assume about these functions? Well, they have to be Schwarz class. There is one more condition that I will say in a second, but the most important condition is that these functions, they should have support only at positive times. Because you see here, I assumed in the easy form of the reflection positivity for 4-point function, I had 2 points lying on one side of the plane and 2 points lying on the other side of the plane. Now you can imagine taking this condition and integrating it against some weight function which depends on x1 and x2, and the reflection of this weight function depending on x3 and x4. But I can only integrate this condition provided that x1 and x2 stay on one side of this plane and x3 and x4 on the other side of the plane. Otherwise, it's not going to work. So I have to respect this property. So I pick these functions f0, fn, which have support only at positive times. So support at positive times in each argument, because we will have again that fn has n arguments, so in each argument should have support at positive times. And then there is one more property that I have to impose, is that I should not, when I do this integral, I should not allow points to collide. So this is something very, very important. So for Whiteman functions with distributions everywhere, including at coincident points. For Schwinger functions, on the one hand, we know that they're analytic. So this is a much stronger than saying that they're distributions. But from the procedure that we described from the analytic continuation, we have no access, we have 0 access to behavior of Schwinger functions at coincident points. So this is something very, very important, because we remember that when we analytically continue, we had to order points in the Schwinger function in some time variable, and assuming that tau1 is larger than tau2. And then we can send tau1 to tau2. We can set tau1 to tau2, but we have no information about what happens when tau1 hits tau2 from analytic continuation. 0 information. And so it means that in this integrated property, we have to assume that f0, fn, they vanish at coincident points. So this is something that I will denote at s non-equal. So vanish at coincident points. Together with all their derivatives. So, in fact, I was not being fully honest. So what I can the only thing we can say about Whiteman functions, about Schwinger functions when we send points to each other, is that they are not going to grow faster than some power law. So that's something that we can show. I'm not sure I have time to show this, but this is something that you can show. But we have no bound on the rate of this power law. So this power law can be very, very high, and if it's very high, then we don't know what happens at the coincident points. Okay, so this is the reflection positivity condition. Yeah, this has to be positive, sorry. For any sequence of functions fn which are supported at positive times and which vanish at coincident points with all their derivatives. So what next? Next comes the Osterwalder Schroeder reconstruction theorem. So I already mentioned this Whiteman reconstruction theorem, which says that if you know Whiteman functions and their properties, then you basically know everything you need. So Osterwalder and Schroeder, they wanted to prove something similar about Schwinger functions. So they said, so they formulated a famous Osterwalder Schroeder reconstruction theorem, which says basically this: if you take Schwinger functions, a collection of Schwinger functions, which satisfy rotation invariance, so Schwinger functions at non-coincident points, which satisfy rotation invariance and they have to be distributions at non-coincident points and everything, and reflection positivity. Then, given these assumptions, in 1972, they gave an argument that you recover Whiteman functions which satisfy all properties that Whiteman functions should satisfy, meaning that they satisfy positivity property and they also satisfy the spectral property. So they have the spectrum and they are Lorentzian invariant. So,
What about Schroeder? You don't have to ask for Schroeder.
well, I said rotation invariance and translation. Yes.
Permutation.
Yeah, so you have to assume permutation, so I think, because permutation is related to microcausality.
Can we get permutation symmetry? I mean, originally our tau 1, tau n are ordered, right?
Well, permutation symmetry, if we are only dealing with identical operators, it's kind of automatic, because you have the same labels phi, 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 phi. So in Euclidean, it's really automatic. But if you're dealing with correlation functions of several operators, phi 1, phi 2, phi n, then and you consider them as functions of x1, x2, xn, and you have a separate access to the function of phi 1, phi 2, phi n, and phi 2, phi 1, phi n, then you can pose the question, well, are they permutation invariant? So in this case, you have to assume that yes, they're permutation invariant. Anyway, there was a sequence of very natural assumptions in Euclidean space, and you get a sequence of Whiteman distributions which satisfied all axioms, all properties that follow from Whiteman axioms, and then you apply the Whiteman reconstruction theorem, and you get the Hilbert space and everything you need. So this is what we call Osterwalder Schroeder reconstruction theorem. Now, it turned out that the first proof of this theorem it contained a subtle error. So in 1975, they gave a second proof of this theorem, a second argument, which corrected this error. And basically, this 1975 paper, it remains the state of the art. So for this result. But given that this error was a bit subtle, it turned out that in order to save the theorem, they had to introduce to the list of conditions one extra condition. So here I gave a list of very natural conditions, very easily understood conditions. But they had to introduce plus extra condition which is called growth condition. In order to save the proof. So without this extra condition, they could not show it. So now the current version of this Osterwalder-Schroeder theorem is that, okay, if you take this natural conditions plus the growth condition, then you can recover Whiteman distributions and everything else that you need. So let me state this growth condition. It's kind of, as you will see, it's a bit weird. So growth on what? It's this condition. It tells you, in a certain sense, how the Schwinger functions Sn, how do they grow as a function of n? So they give you some way to characterize the growth of this Schwinger function as a function of n. So how do you measure the growth of a function? Well, it's a function of n variables, x1, xn. So in order to measure the size of a function, one way to do it, for example, is to integrate it against some test function. Of course, this has to be in our space S non-equal. Although this time it can be supported at any times, positive or negative, not necessarily at positive times. And if the function is not too big, then this integral, it has to be bounded by some constant times something which measures the size of this function f. So how do you measure a size of a function in the Schwarz space? Well, there are the standard way to measure the size of the function in the Schwarz space is this. You take some positive integer n, big N, and you say that you take the function and its derivatives. So you take, say, maximal value of its derivative up to order n at the point x, an absolute value. And then you would like to know that this derivative, what is the size of this max. So what you do is that you multiply this whole thing by 1 over x squared to the power n over 2, big N over 2, and you take the max of all of this over x over all x's on which your function depends. So that's a standard way to measure the size of the function in the Schwarz space. Of course, if you increase this parameter big N, then this measure becomes stronger and stronger because it involves more and more derivatives, and it also involves this factor which depends on x, which becomes bigger and bigger. So the assumption that they had to make is that this thing, this integral, should depend. So here you have to pick some measure, some norm which is of the form constant times n. So we are measuring the size of an n-point Schwinger function. So here it has to be constant times n. And about this sigma n, so now we can ask what is the best possible sigma n. So they had to assume that sigma n is smaller than some constant times n factorial to the power beta. Well, I'm gonna just to take it or leave it. Good question. Yeah. Is there some physical way? Now you can ask. Well, by physical, you can like, for example, take some theory that we know. Take some free theory. For example, would the free theory satisfy this condition? So for free theory, we know that this Schwinger function is just some Wick contractions. The number of Wick contractions grows factorially. So you can show that in that case, you get this condition with sigma growing factorially, just because there are many Wick contractions for free theory.
No, I guess what I meant, so for example, in the CFT, you're going to discuss, you know, that when you take two operators close to each other, you're going to have some OPE, and the power of the divergence of confounded by
Yeah.
the dimensions of the thing. And then you do some fancy integral, I don't know what, and is there some simple direction between power law growth and the point of velocity travel and thing, or does it allow more crazy behavior as operators of travel?
But it's not so much about operators. It's not so much about two operators approaching each other. It's something which involves basically the number of ways. If you take n operators, and it involves the number of ways where these n operators can talk to each other in groups. You shouldn't be worried about two operators. You should be worried about, like, okay, you split the operators into some groups, and these two groups, they can communicate through some channel in the OPE, and then you split it in some other way, and then there's also some channel, and there are many very different ways where, if there are n operators, there are factorially many ways that they can talk to each other. So the combinatorics, there is something which involves combinatorics, but there's also something which involves OPE coefficients. But in fact, that's precisely my point. I see absolutely no way I can check this condition in any theory I'm interested in. So when I learned about this condition, so since this condition appears as a sort of fine print in your credit card contract that you don't read, so already few physicists have read the first Osterwalder Schroeder paper. Even fewer physicists know that the first paper was wrong, because it was appeared in Communications of Mathematical Physics, and of course Communications of Mathematical Physics, it's rigorous stuff, so it cannot be wrong. So even fewer physicists read the second paper, and they know about the existence of any extra condition. So usually we just quote, well, Osterwalder Schroeder proved that it's Euclidean, Minkowski, totally equivalent, end of story. There's nothing to worry about. Now, I was shocked to learn about this condition, because once I learned about this condition, I realized that the theories I'm interested in, like conformal field theories in Euclidean, that I analyze using bootstrap methods, that Osterwalder-Schroeder theorem does not apply to them. Because in order to apply this theorem, I have to find a way to check this condition for all endpoint functions, but I have no idea about a million-point function in the conformal field theory. All I can study is my 4-point function, and I can hope to learn about it. Yeah. For 3-point function, it's obvious, because you take 3-point function, there's going to be for 3-point function, it's going to be obvious. There's going to be some function, some constant sigma 3. There's going to be some finite number. You can compute it. You take 4-point function. It's going to be sigma 4. But this does not bring you closer to the.
I guess my question is that I don't want to necessarily assume something.
What do you mean you don't assume a PE? I assume a PE. I'm going to assume bootstrap axioms. If you don't want to assume a PE, it's another course. You have to invite someone else. Let's say if your Schwinger functions have power law bounds at coincident points, then it's enough for you to know that this inequality is going to be satisfied for each n with some constant sigma n. But it does not tell you how sigma n grows at large n. And this theorem, this stupid theorem, it tells you that you have to know how sigma n grows at n equals a million and higher in order to make some statement about the 4-point function. This looks crazy. Now, I mean, it looks so crazy that with the help of Jashin, we went to see like into the guts of the theorem in order to understand like why do they need this this crazy condition? Why, in order to analytically continue 4-point function, I have to know something about a million-point function? And actually, that's probably the last thing I'm going to explain today. Why they need this condition, and then in the rest of my lectures, I will describe a construction which completely circumvents their argument in the CFT context, and how to analytically continue 4-point function to Minkowski space without ever knowing anything about a million-point function. That's something that I will show in my next lecture. But I think it's instructive to know why, in the general context that they work in, which is quantum field theories, not conformal field theories, you really need something like that. So where does this come from?
By the way, this condition isn't to guarantee that you can construct WNs, or is it to guarantee that you were already able to construct them, but they don't satisfy all the axioms that we assume for the WN?
This condition is needed to construct WNs as distributions. Yeah. So so let me give you some ideas about how this reconstruction theorem is proven. In fact, so there are several steps. The first step is so you start with this Osterwalder Schrader, or you start with the Schwinger functions, which are just functions, and again, so even already at the first step, you would like to bring in the Hilbert space. So as a first step of this construction, you would like to realize the Hilbert your Schwinger functions as functions of some operators acting on the Hilbert space. So how do you do it? Well, you do it by essentially the same trick as for the Whiteman reconstruction theorem. So here there is a lot of similarity. You say that my reflection positivity says that certain integrals which involve sequences of functions are positive. So let me just take my Hilbert space to consist of sequences of functions, and this is my vector space. On this vector space I define an inner product, which is just what you see on the left-hand side of the reflection positivity condition. And so I have this way I have a Hilbert space. And if you follow this logic, you can basically you can make some progress. In particular, you can write any Schwinger function. So we have a Schwinger function, which is just a function of x1, xn. You can write it let's split these 2 points into groups, these sets of points into groups. And you can write this any Schwinger function as an inner product of 2 vectors in this Hilbert space that you constructed. And here you also prove that on this Hilbert space there is a time translation generator, Euclidean time translation generator that you call Hamiltonian. And you prove that the semigroup of translations is a contracting semigroup. So there is a generator which is a positive operator that you call Hamiltonian. So you already start like seeing a lot of things that you expect from the Whiteman axioms, and so you can write this equation. So this equation you recover. So this equation that we are happy to write as physicists, they can recover it in a completely mathematically rigorous fashion. So far so good. This is like this is 1 page. This is not even so hard. Now it looks like we are doing a lot of progress, because now we can take H as a positive operator. So we take analytic continuation, tau goes to tau plus IS. Or maybe let me write it IT. And it looks like we are making a lot of progress. Now we just, if we could send tau to 0 for finite t, this would correspond to the Whiteman functions. But of course, in this limit, when you send tau to 0 for finite t, when we recover these Whiteman functions, we know that the Whiteman functions are not going to be functions, they're going to be distributions. So we have to control this limit. So we have to control the limit, tau going to 0 limit. We have to show, and this is one of the main difficulties in the proof, that when you take an analytic function and you send this tau to 0, you get something which is a distribution. Now, I'm going to, in my subsequent lectures, I'm going to talk a lot about this problem in other contexts. But basically, what this amounts to is that you have to get some bounds about how, so in this limit that tau goes to 0, things can blow up, and you have to get some bounds on how fast they can blow up. So how can you get some bounds on how the things can blow up in this very general context? Well, let's consider some examples. Suppose that I'm dealing with a 4-point function. So then I will have like one state which involves just 1 point, and I will call it psi3, which involves 3 points. And I have to study how this thing, what does this thing do in the limit that tau goes to 0. What I'm going to do is that I'm going to apply Cauchy-Schwarz inequality. So I'm going to say that this inner product is smaller than psi1, psi1 times psi3. No, sorry. Okay, I split it as I split the tau as tau over 2 plus tau over 2, and then I have this I have something like that to the 1/2 by Cauchy-Schwarz. So what this inequality means is that I can get some bound on the analytic continuation of the 4-point function, but this bound is going to involve in the right-hand side a 2-point function times a 6-point function, because psi3 is a 6-point function. So this explains how in the argument, even if I'm just interested in the 4-point functions, the 6-point functions necessarily come into the game through this sort of stupid Cauchy-Schwarz inequality trick. I mean, it's stupid, but given the generality of their construction, the number of tools that they have at their disposal is very, very limited. So yeah, they do what they can. Okay, so we got 6-point function. So we have to know something about 6-point function if you would like to analytically continue 4-point function. But where's the million-point function? Well, here comes another complication that they have to deal with. Is that this argument that I just described to you, when I take tau to tau plus it, it analytically continues in each Euclidean time separately. Because I took one Euclidean time tau, and analytically continues in it. Now, it turns out that for everything to work, we have to be able to take all time separations, and analytically continue in all of them simultaneously. Otherwise, things don't work. Okay, just let us take this. What does this imply for this whole strategy? Well, it implies, suppose that I'm analytically continuing this time, but I also analytically continued in some time separation which was inside psi3. So it means that in this 6-point function that I have in the right-hand side, this psi3 already sits at some analytically continued coordinates. So it's not a Schwinger function. It's an analytically continued Schwinger function. But I started my theory with the Schwinger functions, my theorem. So if this is analytically continued, I also have to estimate it. So if I want to estimate this 6-point function, which is analytically continued, I have to run this Cauchy-Schwarz argument again, which will bring 8-point function. Then I will have to go again and bring 10-point function, and so on, and ad infinitum. So in fact, the way this argument works is that in order to analytically continue from Euclidean to Minkowski, you don't continue this in one step, but you perform an infinite sequence of steps, and every time you apply some Cauchy-Schwarz inequality, and every time the order of functions that are involved is increased. And so by the time you analytically continued all the way to Minkowski, you used all n-point functions. And this estimate, this factorial growth condition, okay, this is basically retrofitted in such a way that when you do this inductive argument, then everything fits nicely together, and you get some estimate in the end. So this is very hard to explain. I'm not sure I'm able to explain it. So what this, the way I read this whole story is that, yeah, if you want to do it in the QFT context, there is really nothing much that you can do. You have to live with this, and you have to somehow find a way to argue for this growth condition. But what we will see in the next lectures is that in the CFT context, we are more powerful, and we will be able to do the analytic continuation for the 4-point function just by itself. So this is the plan for the next lecture, but for today I think everybody is exhausted, so good time to stop.